Assalamualaikum, sir. Hello, everyone. My name is Mohammad Arifin Hashem Walid. I am a student from Department of Tripoli, AIUB. At first, thank you very much for to our honorable sir for giving me the opportunity to represent a presentation on the way computers add numbers. So, at first, we will be introduced with how basically computers add add numbers. Adding numbers in a system is one of the most important application in a computer system. In our daily life, there are billions of work is done in computer system by adding numbers. An adder of summary is a digital circuit that performs addition of numbers. In many computers and other kinds of processors, adders are used in the arithmetic logic units (ALUs). They are also used in other parts of the processor where they are used to calculate addresses, table indices, increment and decrement operators, and similar operations. So usually we use decimal numbers for addition, but computers only know binary numbers. They perform addition using binary numbers also. So computers basically takes input as decimal number and encode it into binary number using encoder, and then performs addition operation by a adder circuit and display the resultant value using decoder for binary to decimal conversion. At the next slide, we will be introduced with methodology. So we build a circuit for explaining the operation of computers system, how they add numbers. We build a 4-bit adder logic circuit using Tinkercad and connect the output terminal of 74HC to 834-bit adder IC to a segment decoder, and the decoder is connected with 7-segment display where we may see the output of 4-bit binary numbers addition. So at the next slide, we will be introduced with the components are required for the circuit. So at first, there is a 74HC283 full adder IC and one breadboard, three 1.5 volt AA batteries, LED lights, resistors and wires for connections, and a 7-segment decoder with a 7-segment display. Thank you so much, sir.
Assalamu alaikum, sir. I am Tahmid from Computer Science Department. As Walid said, our presentation topic is on the way computers add numbers. Now these are the schematic diagrams of the circuits we have designed so far. As time is short, it will take time to discuss these diagrams. So let's move on to the next slide. The next slide is also the schematic diagram of this circuit, which is sheet 2. Here we can see that we have used some switches and resistance and a adder, which I will discuss in the next slide. This is the device we have designed using Tinkercad. At first, we added three 1.5 volt batteries. Total is 4.5 volt. Then we add 8 switches and 13 LED lights. Then around 13 resistors with 220 ohms resistance. We have used 74 AC283 adder to add two binary numbers in this device. This device will add two 4-digit binary numbers and will also convert it to a decimal number. This is how a computer adds two numbers. In this device, as you can see, the switches will give the signal high and low as 1 and 0. The device will take the signal from LSB to MSB. We have total 8 inputs. First 4 inputs we have shown using orange LED lights, and second 4 inputs we have used blue LED lights, and the 5 outputs we have used red LED lights. There are 5 outputs. One of the output is carry bit. Then the output will convert 5 outputs will be converted into a decimal number. That's all from my side. Now Jahid will discuss the logic diagram.
Assalamu alaikum, sir. I am Jahid Hassan Talukdar Onik. My ID is 2042422841. My previous member Talha is already explained about the schematic diagram operation of the circuit. Now I am explain about the logic diagram and pin configuration of 74HC283 4-bit binary adder. The 74HC283 is a high-speed SI gate CMOS device and is being compatible with low-power Scotty TTL, ASL TTL. The 74HC283 is specified is compliance with JEDEC standard on 7A. The 74HC283 adder two 4-bit binary words and plus BN plus the incoming carry CIN. The binary sum appears on the sum outputs S1 to S4 and the outgoing carry Cout according to a equation. Due to the symmetry of the binary at function, the 74HC283 can be used with either all active high operands positive logic or all active low operands. In case of all active low operands, the result S1 to S4 and Cout should be interpreted also as active low. With active high input, CIN must be held low where no carry is intended. Interchanging inputs of equal weights does not affect the operation. The CIN A1, B1 can be assigned arbitrarily to pins 5, 6, 7, etc. Now I am explaining about CD4511 7-segment decoder truth table and its truth table pin configuration and symmetric and schematic. CD4511 is a BCD to 7-segment latch decoder driver IC formed with CMOS logic and NPN bipolar transistor output devices on an immovable structure. 7-segment display widely used to project numbers in many applications, and here is the simple driver circuit to convert BCD to 7-segment display. Designed by using CD4511, it can drive common cathode 7-segment display. Thank you, sir.
Hi everyone, my name is Shahidul Hassan and my ID is 194071. Today I am going to present about 7-segment display, that is the decimal numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and already it displays A, B, C, D, E, F, G. For 0 here is A, B, C, D, E, F are constant expect G. So here is G is 0 and A, B, C, D, E, F is 1. For a decimal number 1, here is A, here is B and C is constant, so it is 1 and F and A, D, E, F, G is 0. For decimal digit 2, A, B, D, E, G is constant and everything is 0. For decimal number 4, B, C, F, G is constant and everything is 0. For decimal digit 5, A, C, D, F, G is constant and B and E is 0. For decimal digit 6, A, C, D, E, F, G is constant and only B is 0. For decimal digit 7, A, B, C is on the state and everything is 0. For decimal digit 8, A, B, C, D, E, F, G is on state, so everything is 1. For decimal digit 9, only E is not on state, so only E is 0 and everything is 1. Here is the conclusion part. Adders are very important in our daily life. Adders are used in different way, and adders are used in processor and a graphics card, and many expression are easily explained by adders. Thank you everyone.